All right, so AP Calculus. We are talking about the cylindrical shell method of finding volumes of solids of revolution today. So I want to just compare and contrast two methods here. The washer method, where we find a volume of a solid when we have an area, and we basically just swing that area around an axis, either this way or this way, right? We just swing it around, and as it makes a path through space, it carves out a volume, or it carves out a volume if you rotate it this way, okay? So it would be like this water bottle right here. If you could only see half of it, and this was your region, okay, right here. You've got some kind of, or let's maybe put it on the side, put it sideways, so that it, so that you can see this part, okay? And it's a let's say it's a logarithmic function or something, right? Kind of see it? Maybe I'll switch it around like this, okay? And it's a log function. Well, if you were to rotate that around this x-axis, the edge of the white paper, you would get this bottle, right? So here's the upper function, and you've rotated it around, right? Similarly, let's say you have like a quadratic function that looks like this, okay? And if you rotate it around the y-axis, you get a solid that's carved out in space like this, okay? So this is what we've been doing, and I will show you this right here. If we are rotating this region R around this axis, x equals -1/4, the vertical axis, then we are taking this thing right here, and we are swinging this around in space, right? It's coming around in space like this. It's going like this, and we're making a bit of a cone. Sorry, we're making a little bit of a kind of like a speaker or whatever. It looks like this. This is what it is. Okay, so here is our y-axis. Here is our x-axis right here. Right. Here is our line x equals -1/4, and this is what you get. You take, and here's the original area, right? Okay. So this is all a review of what we've done so far, and that's an excellent way of envisioning how that solid could be carved out. Well, I want to just throw your thinking, I want to just mess you up right now, okay? I want you to think about this a little bit of a different way. Instead of taking a region and swinging it around and carving out space, what I want you to do is I want you to think about the cylindrical or cylinder shell method. And what that is we start off with cylinders and we consider the wraparound part, the sleeve of the cylinder. Now in this diagram over here on the right, you can kind of see already that we have a bit of a cylinder already, carved out. So this would be the middle part of this solid of revolution, right? But you can kind of see that that's a cylinder. Now I'm not interested in the space inside. In fact, that's empty. It's empty space inside. So I'm not concerned about that. But if you consider the external wraparound part, this wraparound part of this cylinder, that's going to be part of that volume of solid of revolution, part of it. Now we need to actually take the cylinder now, and we need to consider another cylinder that slides over top of it, but that's a little bit bigger, okay? And then another cylinder that slides over top of that and is slightly bigger yet. And so instead of stacking discs or washers this way, we're stacking cylindrical shells out this way. Okay? So think of it that way. Now, let me just draw a few more just to help you visualize this. So obviously the next cylinder, okay, I'm going to make them really thick and space them out a bit, but the next cylinder is going to have to be a little shorter. You see, because I'm going from here, from here all the way around to here. And we're still just going down to the base. There's a bottom, a clear bottom, but it's going to be a little bit wider, right? And so here you have a cylinder that is wrapped around, it slides over top of the previous cylinder, but it has to be smaller. And yet again, I'm going to take another cylinder that's smaller yet, but that still goes down to the same bottom part here, the bottom of this volume. And it's going to be shorter and really wide, you see? Okay, so there's this one. Whoops. And it's going to come, this is kind of tough to draw. It's going to come down here like this. Okay, now with the blue one, of course, this blue one, it wraps around the backside as well. So if you consider all of these cylindrical shells or cylinder shells, we're going to keep going forever here. We could, I mean, really, yeah, forever. But you see how it gets really short but really wide out near the edge? Okay. So a really short cylinder but really wide. Okay. And if you stack all these up, this becomes, at the very edge, becomes something that's so very small. It really is just it's almost, there's no height to it at all, right? Like super short. Now, I'm barely even going to draw that, right? Just think of it as a cylinder that the cylinders, the heights go like this, and they kind of like squeeze out to pretty much zero at the end, right? But it's a really wide, with no height, the cylinder almost. So this is the cylindrical shell method. Instead of taking a region and swinging it around an axis, we're taking shells and we're stacking them. We're stacking them around each other until that space is filled up. Another way to look at it, okay? Another way to look at it. Now, what's really good about this cylindrical shell method, and the reason why we need to learn this, is because, I don't know if this is the same for you, but for me, it's a bit awkward when I do like integrals dy. You have to, this is no good. You have to like isolate for x. Okay, well, who isolates for x? That's crazy. The functions are in y, right? So you have to isolate for x. You have to turn this into x equals something y, and y squared, blah blah blah, right? So then you have to put that in there because it's got to be something y dy, and you got to do pi, and this has got to be squared and all that stuff. So the dy is a bit awkward, and how do you remember that, right? So these are obviously going to be y's as well. So that's one way, and you guys are good at that. You're good at that. But watch this. If we use a cylindrical shell method, okay, and I'm going to erase some of these cylindrical shells, but we're going to use integrals obviously still. But how do we split this up now? Well, think about this. The radius, okay, first of all, a cylindrical shell. Do we want to use volume? Nope. We don't want the inside part of the shells. We just want the outer wraparound part. So if you remember, here's a little net diagram just to give you nightmares back from, Foundations 10 or whatever math class you learned these in. Here's a net diagram. So obviously we have pi r squared here, right? Here and here. And this length right here, or the wraparound part, that would be the, the circular top of the cylinder, is going to be what? 2 times pi times r. All right? So that's the length here. Okay, 2 times r. Now, what about the height? Well, the height is just going to be h, or height. So this area here for this thing is going to be 2 pi r h. And that's what we're concerned with. We're not concerned with the top or the bottom. We're just concerned with the wraparound part of each cylinder. So the radius. Okay, the radius, if we're wrapping around the y-axis, the radius goes out in this direction. Well, what measure is that? The horizontal. That's the x. So guess what? The radius equals x. Boom. That's nice. So this part is equal to x. I should back up. What about 2 pi? Constant. Awesome. So we've got 2 pi as a constant. Guess what? That's going to be outside of our integral. Just get it out of there. Just remove it. Put it out front. We're going to multiply later. The r is x. Okay, so whatever you're, and not the function in terms of x. No, just x itself. Because the radius is going to change as the x changes. Okay? Now in this particular case, this is special. This is, okay, now this is sort of level 2 that I'm starting you with, all right? We're not rotating about the y-axis because that would be, the radius would be exactly x. Whatever the x is, that would be the radius if we're starting from 0. Okay? And that's what this represents. But if we're actually starting from, -1/4, then the radius, okay, is going to be x, whatever x is, plus this bit. So it's actually going to be x plus 1/4, or 1/4 plus x. Okay? So if we're rotating about an axis that's not the y-axis, then you have to consider the radius is from the center of rotation. Okay? So you have to add on whatever is not just the x values. Okay, so in this case, we're going to do 1/4 plus x. Okay, We can talk a little bit more about that later, but I don't want to get too far into details here. I just want to give you high level stuff, okay? So the radius this way is x. The radius of the shells are x. That's important. So if the radius is x, and what about the little differential, the little width of each of these shells? Well, that's in this direction again, so this is dx. So guess what? I mean, notice this, okay? Here's what. The washer method is dy. Everything's y, kind of backwards. The cylindrical shell method, for going the same way, is all dx. So it's opposite. Something you're going to have to just remember. Now, the h here. Okay, so the h is easy. The h is simply from, the bottom here, which is going to be just the x-axis, all the way up to y, all the way up to this right here. So the height will change as we move out from 0. The height is going to change. It's going to get smaller and smaller and smaller in both directions, right? So the height is simply going to be the height of the function. And if we go down to a constant down here, well, it's going to be the function plus this. If we just go from here, it's going to be the function minus that, so we can adjust that, but right now it's just the height of the function. So the height of the function is 1 minus root x. So I don't have enough room here. 1 minus root x. 1 minus root x. That's the description of this right here, dx. Okay, so I've got my cylindrical shells, all right? One cylindrical shell will be 2 pi rh. There's 2 pi. Here's my r. Here's my h. And of course, this r and this h are going to vary as x changes. And I've got that accounted for. The radius will change and the height will change. Beauty. The last thing to consider here is the limits of integration. Okay. So if we have dx, am I going to have x values or y values here? Dx, I should have x values here. Okay. X values. So what are the x values going to go from? From what to what? Well, if you aren't given this, I guess, if you aren't given this, you're going to have to check to see, what this value is and this value is. In this case, we know that this is 0 and this is 1. So it looks like our limits of integration. So where do we start our first shell? Okay, is at x equals 0. The radius then will be 1/4, you see, for the first one. 0, 1/4. 0, 1 minus 0 is going to be 1. So this is where we start at 1. See that? For height. So the first shell has a radius of 1/4 plus 0 and a height of 1 minus 0. Okay, and that's where we start. And then we're going to move out to 1. So this looks like to be 0 to 1. All right, so that's what we have here so far. That's the introduction to the cylindrical shell method. It's the 2 pi rh, very important, 2 pi rh, okay? Now let's do an example, okay? Let's do our first example here. And I think on another video of mine, I've done this question. And when you do this question with the washer method, guys, the washer method, it's actually quite difficult. It's a combination of the disk method and the washer method. So before we do the cylindrical shell, I'm just going to really quickly, watch this, really quickly. If we were trying to find, okay, so here's the area here. What do we got? Y equals x plus 2, that's this one. Y equals x plus 2. And y equals x, okay? So the boundary in between these two and in also before x equals 3. So here's x equals 3, this vertical line, okay? So here's my region. Now, we're going to wrap this around the y-axis. So we're going to go, so it's on a bit of an angle here like this, right? And we're going to wrap it around like this. And we're going to cut out this swath kind of like a big thick V out of space. Now, with the washer method, before the shell method, this is how difficult this is. And honestly, this is a bit crazy. You have to separate this into 3 sections. That's what you have to do. Here's section number 1. The reason is because we have this function right here, and we have 0. So this is going to be the disk method, and we have to find this volume first, okay, as this rotates around in space. Okay, got it? That's part 1. Part 2, we move now to the washer method, which means that we have 2 functions to deal with, and so we do the integral, and we would do, pi integral x minus 0 squared minus x plus 2, minus 0 squared. So we'd have to do the washer method. But we only can focus on this region. Here, I'll do this in black. We can only focus on this one. So I do washer method. Why? Because here's function 1, here's function 2. I can't go any further because now we have a third function over here, right? So I have to swing this one around, okay? And so it comes in pieces. Not impossible, but not easy. And so finally part 3 says I have to now take this region and I have to swing this one around. And you're thinking, my goodness, that's a lot of work. Well, it is a lot of work. But with the cylindrical shell method, I'm happy to announce that our lives will get easier. Yes, cylindrical shell method. Make my life easier. Yeah, buddy. Okay? So, how's that going to happen? Well, we don't have to mess around with 3 different sections: disk, washer, all these different functions. I can envision, and here's what I'm going to do. This whole region right here is going to be rotated around the y-axis. And so I'm going to envision myself here a tiny little cylinder. Here's my first cylinder that I'm envisioning. Not down to the bottom quite. I can't draw this, sorry. But there's my first little cylinder. And guess what? I'm envisioning another cylinder that kind of goes like this. Okay? Just down to here. As I work up, I have these cylinders that look like this. Okay? And it just goes down to the, see, it doesn't go all the way down to the x-axis or anything. But you have these cylinders, and here's my final big one. Okay? Okay? Maybe this is working for you. Maybe it's not. But you see, all I'm dealing with now is the difference between the 2 functions as they go upward. I guess this is for you guys this way. Okay? So my height is the difference between the 2 functions. That's it. And it works all the way across. So, the cylindrical shell method. Okay. The volume here, rotated around, is going to be a collection of, and here's the collection of, right? Cylinder shells, which we know the area of cylinder shells is 2 pi RH, 2 pi, constant. Thank you very much. I'm going to put you out there. Okay? And the thickness of these shells are in the horizontal direction. That's dx. So I got an indication here. This is going to be dx. Awesome. Okay. Nice and easy. So that means, hey, that these values here have to be x and x as well. Now, if I wanted to take a bunch of shells and work out, and I wanted to consider x values, where am I going to start and where am I going to stop? Well, I'm going to start at the very middle here. Okay, I'm going to start at x equals 0. X equals 0. That's where I start. I'm going to have this cylinder shell that's like a radius of 0, right? But then we're going to work up from 0, which really doesn't exist. I know, it's a solid line. But then we're going to work out from that. And as the radius comes a little bit larger, like 0.000000001, we have this height, and we have this first little shell. Okay, so we're going to start at x equals 0, and we're going to go to what? X equals what? 1? No. 2? Nope. We're going to stop at this right here, where it says x equals 3. So I'm going to go from 0 to 3. Okay, my shells are I'm going to have the stack of shells from 0, where I want to rotate around, to all the way out to 3. Okay, so 2 pi. Now r. Ooh, r is easy. The radius comes from 0 all the way out to going to 3. Those are the x values, straight x values. Guess what? I put an x right here. Boom. 2 pi r, radius, my x values. And what's my height? Well, the height is the difference between these 2 functions. And these 2 functions are straight lines, so that's easy. It's going to be the same height all the time. But even if there was 2 different functions, guys, watch this. Okay, if I had a function like this and a function like this, crazy. The height is going to change as x changes, but guess what? As long as I have descriptions for those 2 functions, it's simply the difference between the top function minus the bottom function. It's pretty easy. So the height is going to be x plus 2. Don't put the y in there, guys. Don't put the y, remember? Just x is here. X plus 2 minus x. Okay? Cylindrical shells. Okay? All right, so let's keep going here. And then the volume, we can simplify all this. Okay, 0 to 3. This is going to be x times what? What's x plus 2 minus x? Well, that's just 2. So this look like 2x to you? Huh? Does that look like 2x? Looks pretty easy, man. So what this is saying is that the height here between these two is always 2. Does that make sense? X plus 2, 2. This is 2, this is 0. I mean, it's always 2. So it's just 2 is the height. The radius changes as x changes. Okay? All right. Well, this is great. We can do this by hand. We don't need a calculator for this. What's the integral of 2x? The integral of 2x, we're going to add 1 to the exponent. That's going to be 2 over 2x squared, right? Add 1 there, divide by the 2 as well. And then we're going to take that from 0 to 3. So what does that give us? Well, this is 9. So that's just a 1. 3 squared, 9 minus 0. Volume is 18 pi units cubed. That's the volume. And that is your correct answer. Okay? All right, so that is your first example with the shell method here. Let's do this one. This is question number 8 from your assignment. And if you're in my class, you did this question, or should have done this question. And you rotated, you used the disk method, you rotated around. Let's do the shell method, okay? Let's get some practice, a little bit more practice here. So I don't want this area, okay? I don't want the shells to fill this area here. I want the shells to fill this top area. So guess what? The height is still going to be the difference between the top function and this function. It's not going to be the bottom function and the axis. We have to be careful with the height there. But other than that, everything else should line up to be the same. So let's give this a go. So volume is going to be, we're going to take a collection of cylindrical shells. I know that I'm going to do 2 pi out here. Okay. This is going to be dx, because why? Because it's around the y-axis. And you know that swinging around the y-axis, cylindrical shells are dx. Why? Because the shells themselves, oh boy, what is that? That's an oval. Okay, come on, Max. Okay, here we go. Okay, the little thickness there, the thickness of those shells is in the x direction, so that's a dx, you know that. Okay, so 2 pi, what's r? Well, r is going to start at 0 and go to 3, the radius, right? 0 and go out, keep going out to 3. So we've got r is x. I can do, let's do the height. So the height is, for this question right here, the top boundary is y equals 2. And the bottom boundary is, oh, they've got x equals. Guess what, guys? Guess what? For the disk method, this is great. We don't want this. We don't want this for the shell method. We need y equals, okay? So let's just do this. 2x equals 3y. Y equals 2x over 3, or 2/3 x. Okay? So we need to get y by itself because I need this as part of the height. So I've got y equals 2. So the height is going to be 2 because, height is going to be 2 minus this function right here. So the height should be 2 minus 2 over 3x. Okay? 2 pi r h. Height of those cylinders. Now, the limits of integration, right? Okay, x is their radius, dx, right? So these are x terms. And I'm going to go from an inside, I'm going to start calculating my radius from 0. And I'm going to go all the way out to 3. All right. So if we continue our calculations here, I'm going to simplify this, I think, a little bit. This just seems like I don't want a product there. So 0 to 3. That's going to be, what, 2x minus 2/3 x squared. Okay, I'm going to distribute that. You can distribute that in because that's all one thing. I mean, I don't need to tell you this, but, you know, that's just all one blob, and you can just simplify that blob if you want into a polynomial. That's great. So dx. So now I can go ahead and take the integral. I can go ahead and do this now. Whoops. Oh gosh, what the heck did I do? Okay, there we go. Okay, 2 pi. And the integral of 2x is going to be x squared. Right? You know that. This integral right here, we're going to up this to 3. And I'm going to divide by 3 again. So this is going to be minus 2 over 9 over 3 times 3. x cubed, right? Because if I take the derivative of this, I get 3 times 2 over 9 x squared. 3 and 9, that's 1, 3, 2/3. Okay, there we go. And from 0 to 3. So real quick. All right, so we evaluate that, and we get 6 pi cubic units for our volume. And that is, there you go, there's your answer right there, I guess. That's 6 pi. Okay? You don't really need the units cubed there. I like that. I mean, I'm a science guy, and, you know, I like units. Units, pretty good. But I understand what we're doing. We're doing volumes here, so don't worry about the units cubed. If you can do that, great. If you forget, don't worry about it. Okay? Any questions about that? Anybody from my virtual class want to chat in with a question about that, or do we understand that fully? Because I'm going to give you another example, another question to do here on your own. So if there are no questions, okay. So thank you, Kara, for this question. Very good question. Is the shell method ever used when an area is revolved around the x-axis? I am going to get to an example like that, and the answer is, of course, yes. But instead of the shells being upright, sort of thing, the shells are tipped over, and they're like this. So guess what? The radius will be kind of like the height, and the height will be kind of like the, you know, this. The height will be like the radius. It's flipped around. So yes, I think the strength of this is when it's revolved around around the y-axis, because you can use dx stuff, and it's more familiar. Okay, so let's do this one here. Okay, this might look a little trickier with the tan 1/4 y. But okay, and this is an x2, so I might help you with what this tan equals, okay? But try this one. And again, this original question was asking students to do, and you guys have done this question, I think, in an assignment, to do it with the disk method, okay, the horizontal disk method. But I want you to do this with the shell method, all right? So go ahead and give this a try, and I will show up on the screen here, you know, what this equals as far as, you know, when we isolate for y or whatever. I can help you with that. But why don't you go ahead and give this a try. And this is number 9, your text. There should be your answer. So try the shell method for number 9. All right, so in a question like this, if you had to choose between the shell method and disk method, you might want to use the disk method just because this is going to be a more familiar equation. But with the shell method, so here's what you have to use. You have to do tan to the -1 x equals pi over 4y. Okay, so we are going to, and tan to the -1 is like arctan. Okay, remember that? So we worked with those a little bit before. So this is going to be 4 over pi arctan x equals y. Okay, so you will need your calculator to do this integral, all right? I won't, you don't have to, I mean, you can do this by hand, actually. I think we have done integral of arctan for derivatives anyways. So there's your function though, okay? So remember now with the height of these cylindrical shells, okay? The height is going to be y equals 1 minus this function in terms of y, not x, okay? So right here. Okay, so go ahead and give that a try. 2 pi RH, give it a try. All right, so hopefully you've had a chance to take a look at that here. One of the important things that I didn't go over before I let you start was this integration, the limits of integration. Obviously, we're going to go from 0 here, right? But the radius is going to go out to what? Well, what is this point right here? We don't know what this point is. So we have to figure that out. And this is a y equals 1. So guess what? If y equals 1, we just put a 1 in there, and then x equals tan of pi over 4. So tan of pi over 4, if you remember on your unit circle, sine and cos are the exact same. At pi over 4, it's 45. So root 2 over 2 divided by root 2 over 2 is 1. So x equals 1 here. And that's how I get my upper limit of integration there. I also just did this on my calculator here too. If you, where is it? So if you type in, again, I just focus on this right here, okay? if you type in this as an equation, x times 1 minus 4 over pi tan to the negative 1 of x, and you graph that, okay, then it'll come up with this line when you zoom in a bit, and you want to find the integral, or the area underneath the curve, from 0 to 1. So I did that, and I found that the integral was 0.1366. That's where I got this number from. Okay, so this right here, this value from my calculator is this value. Okay, right there. Multiply by 2 pi, and you're done. Okay, that's going to be your. Now I know this graph right here doesn't look like this graph, but remember this is the inverse. Okay, this is sort of the inverse there. Well, it's not quite the inverse. It's this graph right here. It would be this function right here. So it has nothing to do with this one other than it's part of the solution there. Okay, so it's not supposed to equal that. Okay, any questions about that online class? All right, so we're going to do number 7 from the textbook here, and you've already done this one with the using the disk method. So you've done it like this. So this is like a cone, right? And here you go. You've got this, imaginary line here, and you've got all these disks, right? So you've done this pi r squared, blah blah blah. Your r is your y, and it's dy. Now, dx, sorry. So with this one, but with the cylindrical shells, okay, you can still use the cylindrical shell method here, but we are not rotating it around the y-axis. So our cylindrical shells do not look like this, right? With these heights, don't look like that. Instead, they have to be tipped over, and so the middle of the cylinder has to be the axis we're rotating around. So it's like this, right? Ish. So the cylinders are now on edge here. Okay. Okay. And again, this is. I don't know why I drew that one straight. Okay. So you get the picture, right? Okay. So they're tipped over on the side now. No problem. We just have to be careful. So again, we've got v equals the integral, we got 2 pi times the integral of 2 pi r h, okay, and d whatever. So if we have this as a bit of an outline, I'm going to fill this in and this in and this in, and I'm going to change these two. As a bit of an outline, okay, the thickness, I don't know how you like to think of this. The thickness, okay, is this dx or dy? Well, the thickness is in the vertical dimension. So this is going to be dy, okay? dy. R, what about r? R is going to be the distance from here out. So does that look like x values or something else? Well, that's y values. So this is y. See that? Let me rewrite this now. Okay, so y and dy. So what is h? Now h, the height, is actually, this is a tipped over cylinder, right? So the height is going to be the difference from this function down to y equals 0. Now for dy, we have to express these functions in terms of x. So they have to be x equals something, 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 y something, right? So I'm going to have to solve for x here. No problem. That's going to be negative 2y plus 2, or x equals 2 minus 2y, whatever you like, whatever. So that's what this function is going to be right here. Let's use this one. Okay? So the height is now going to be, and it's going to be, of course, this minus 0, whatever, right? Because 0 is the is the bottom here. We're not talking about this as the bottom. We're talking about this as the bottom. So we have, I'll change to blue, 2 minus 2y. And our limits of integration, okay, if this is dy, guess what? This has to be y and y. So we are going to stack them like this, right? We're going to have our cylinders stacked like this. And it's going to be in the y direction, so we're going to start from here, and we're going to go up to, looks like 1, right? So we're going to have a really thin one, and we're going to stack them all the way from 0 to 1. All right? Okay, so now we can, we don't have to use a calculator for this. This is easy. We could do this by hand. So this is going to be 2y minus 2y squared, I guess, dy. And so our volume is going to be 2 pi times, now I can evaluate this integral, It's a definite integral, so let's evaluate it by first finding the antiderivatives here. And so this is going to be y squared. And this is going to be, what, 2/3 y cubed. And we're going to evaluate that from 0 to 1. So we got 2 pi, and we've got 1 minus 2/3, and then minus 0 to, minus 0. So we've got our volume is 2 pi, and 1 minus 2/3 is 1/3, right? 1/3, right? That's 2/3. So we should have a volume of 2 pi over 3 cubic units. And if you recall, and there's our answer right there. If you recall now, there's actually, yeah, there is 3 ways of doing these, right? This is a cone. That's a cone. Okay. Now think about this. Think about this. It's got a round bottom, right? And it's like a circular pyramid, right? So that's a cone. So what's the formula for the volume of a cone? Well, it's 1/3 pi r squared h. 1/3 pi r squared h. What's r? Well, it would be r at the bottom. So r is 1. So the volume is 1/3 pi times 1 squared. And what's the h? 2. Oh, really? So what's that? Well, that's 1 times pi times 1 times 2 over 3. That's 2 pi over 3. So there we go. Now you're thinking, why don't we just use like grade 5 math here? Well, you can, but if you're asked to use the shell method, right, then you have to do what's on the left there, okay? And you can. You can. That's the cool part about it. See, there's multiple ways of solving the same problem in math, right? Because it's just so objective and it adds up, okay? Okay, any questions about that? And of course, I think you did this as well with the disk method as well, so that's a little bit different as well there. And so there's 3 ways of doing the same type of problem, really. Okay, so one more example for you. This is a practice AP question. This is the final question. I'm going to ask you to do this on your own, see how you're doing with this shell method. And I'll read the question to you, and of course it is multiple choice, so the correct answer is up here somewhere. So it says this: what is the volume of the solid generated when the region bounded by the graph x equals square root y minus 2 and the lines x equals 0 and y equals 5 is revolved about the y-axis? Okay, so no diagram is given. That's all that you're going to be given on the test. And I would suggest drawing a quick sketch, making sure the equations are in terms of the right variable. But I want you to do the shell method, and later on we're going to do the disk method as well. So get some practice with the shell method. Take a few minutes, attempt this. I will show you the answer in a little bit. All right, so here is the solution, which I'll walk through with you. What we want to do is, first of all, we want to see what this graph's like. Okay, so using the shell method, right, we know that we're going to use vertical shells. It's around the y-axis, vertical shells, so it's going to be dx. We need things in terms of y. So y equals, right, so in terms of x. So we need to solve for y. So I'm going to do that. I'm going to square both sides. I'm going to get y by itself. So we've got y equals x squared plus 2. So I know that that has a vertex of 0, 2. I know it's a bit of a parabola. It's going to intersect y equals 5 over here. Okay? So I've kind of got this sketched out. You don't have to sketch out the cylinder, but at least I know what I'm looking for. My r is going to be my x values, right? Here's your r values there, your x. Okay? The height is going to be 5 minus my function here. 5 minus x squared plus 2. Okay, so if I'm looking at 2 pi RH, then I'm looking at volume here is 2 pi, and I've got x times 5 minus x squared minus 2. And the limits of integration, okay, so doing the disk method, you don't have to find this value, okay? Using the shell method you do, because we have to go from 0 all the way out to what? So where did I do that? Let's see. Oh yeah, here we go. We got y equals 5, and we got y equals s squared plus 2. So you let those equal each other, and x is root 3. So this is going to be square root 3 out here. Okay, So that's the only kind of weird thing extra thing you got to find doing the shell method for this one. But your integral is going to be, in the x direction because we've got dx. We're going to go from 0 to this intersection point. And that's going to be root 3. So we simplify this here a little bit. I'm going to multiply things out. I'm going to take the antiderivative. I'm going to evaluate here. And you should get simplified to 9 pi over 2 units cubed, which is in decimal form 14.137. Okay. Anybody have any questions about that for me? Okay. All right. Well, that's the end of the shell method lesson. I hope that helped. And remember, cylindrical shells are our friends, especially when we're rotating around the y-axis, because we have the all familiar dx. Our functions can be y equals, just like we're used to. Okay. So there's your lesson on the shell method.